Gonna try this a little differently this time. Sorry you don't get to see my bright and shining face, but one, it'll be easier to read my handwriting, and that's probably the best thing for you guys. So Unit 6, gases. I'm going to talk a lot here to start with about the kinetic molecular theory, and I'll abbreviate that later on KMT, just because it's a bunch shorter. And then we're going to talk a lot about ideal gas. So what an ideal gas is, it's imaginary. So nothing, not real at all. There is no gas that acts perfectly like this, but an ideal gas fits all of the assumptions that we're about to run through. The second thing you need to know, this idea of kinetic. Kinetic means movement. Kinetic energy then is the energy of movement. So our first assumption, that particles and matter are in constant motion. This is the idea of kinetic. So talk a lot about gases here. This allows gases to take the shape of their container. They're in constant motion. They completely fill it. They're not tied down like a solid or a liquid is, kind of to each other. There's no attraction there. Part B of this, these particles are constantly, frequently is the word used here, colliding with themselves and the walls of the container. This causes pressure as they hit those walls. We'll talk about the collisions here in a second. So pressure caused by those collisions with the walls. That's what's pushing out on a container full of gas. Collisions. This is our second assumption. In gases, we assume that all collisions between particles are elastic. Meaning no energy is lost. So picture here, a little physics. Drop a bouncy ball and it bounces to the same height every time. That's what an elastic collision is. I don't know why it's spelled like that. In the other part of this diagram, so something that was inelastic, and this is what we see in reality, as you drop a bouncy ball, it kind of gets lower and lower, and finally it's no longer bouncing. So energy here is lost through heat, through sound, and not what we want for our ideal gas kinetic molecular theory. Third assumption, gases have low densities. You should know this. They feel light for their size. Feel very light for their size, actually. So much so that we use grams per liter to measure their density, not milliliters. What this means, or kind of another part of this, I guess, is these gas particles, again, they're particles, they're molecules. They are so small that we don't even count them in the volume. So their volume is negligible compared to the container. So mostly empty space. Know that part. Part B, this makes them compressible. So since we have all of this empty space, we can push them closer and closer together. Fourth assumption, at a given temperature, all gas particles are moving with the same energy. And that energy, that average kinetic, is dependent upon the temperature. So a cool gas here, they're moving around still because, again, everything is at constant motion. But then as we crank up the heat, you get more energy, which means we get more collisions with each other and more collisions with the wall. And those collisions have more energy as well. So there's more energy. There's more force as they hit the wall. So the hotter the gas, the greater the average kinetic. Fifth one here, there is no forces of attraction or repulsion between the particles. Those particles, if you think about it this way, those particles think nothing else is in the container. They're just bouncing around, not a care in the world. They're not grabbing and holding on to each other, not grabbing and holding on to the container. No attractions for our ideal gas. Well, those are ideal situations, and nothing completely follows all of that. So those 5 things, again, that's an ideal world. We don't live in an ideal world. So in the real world, the more attractive forces a real gas has, the less it fits. So when we start talking about like polar gases, they don't quite fit all of those assumptions. Now, something like a noble gas fits pretty well. They don't bond with each other. They don't need an extra electron, so they just kind of go about their merry way all the time. Why do we care? Well, we can use this idea of an ideal gas to help explain behaviors of real gases. Next few slides here, variables. So help us define a gas. We can talk about a gas in terms of pressure, so definition, force per unit area on a surface, mathematical equation there saying the same thing. And then just kind of an application of that, the smaller the surface area. So if I start dividing by a smallest number here, or a smaller number here, this pressure number is going to get higher. Example, if I stand on your toe with my shoes on, so force is me, area is, my shoe, it's going to hurt. But if I stand on your toe wearing high heels, one, my calves are going to look awesome, and two, this area is going to be a lot smaller with that heel. So force doesn't change, force is me. With a smaller area, pressure is going to go way up and it's going to hurt a lot more. Units for this, area, meters squared, centimeters squared, blah, 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 blah. We're going to use meters squared because that's our SI unit. Force is something called the Newton, capital N, something you don't see a lot. You'll see a lot more in physics. So pressure is newtons divided by area, which is defined as something else. This newtons per meter squared is a Pascal. So dead white guy, this is our unit of pressure. And conversions, yes, sometimes word problems, they will not give you a Pascal, or they won't give you an atmosphere. And depending on, we're going to talk about a constant, depending on what constant is given to you, we may have to do some conversions. One step. Super easy. You just got to know what the equivalency is. So these pascals, so 101, 1.01 times 10 to the fifth pascals, so a lot of them. Pascal is very small. Is equal to 760 torr. Again, another dead white guy. Can't remember. I think he was Italian. And then is also equal to 760 millimeters of mercury. If you've ever read a barometer or something like that, watch the news. They talk about millimeters of mercury sometimes. And then the other one is 1 atmosphere. So that's what ATM, atmosphere, stands for. So atmosphere, millimeters of mercury, torr, pascals. The second variable that helps us define a gas is volume. So how much space is being taken up? Units, you've seen them before. Temperature, another variable, because we know as temperature increases, the average kinetic energy changes. So temperature is a measurement of average kinetic energy, not how hot, not how cold. It helps us, kind of determine how hot or cold something is, but the actual definition of temperature, measurement, average kinetic energy. Units, a new one, so dead white guy, capital K for Kelvin. Easy conversion, so it's a science class, we use Celsius all the time. So easy conversion, just add 273.15 to get Kelvin. What this means is we will never have a negative temperature, which is good because it's hard to have a negative volume or a negative pressure when we start plugging into some equations. So everything should always be positive. If you have a negative number, you use this wrong. The last one, in terms of our variables that help define a gas, is, well, how much gas is in our sample, or how many particles are in a sample? And we use the old mole, which we just finished talking a lot about, units, moles there. So we'll use this information. We'll do some, pressure conversions, like convert 760 millimeters of mercury to torr, or convert Celsius to Kelvin, and back and forth, just to get us set up, ready to go for some other problems, some application of this.